Hello, I'm just doing a little bit of mic testing. Okay, things seems to work. Um, I know it's a little abrupt and it's 2 in the morning. I just woke up and I thought, why not just do this? I have some free time. Um, yeah. So last time I was talking about classification, and although we did train a model, we did not go through the evaluation part of it. That is, like, uh, we haven't talked about the matrix like precisions and recalls and confusion matrix or F1 scores and all that cool stuff, right? Uh, but I want to hold that for a moment as we will be doing a lot of more of classifications and we will be training more models and then I might introduce those topics as well. Yeah, and this is so this stream would be more of learning for me and learning for you guys as well. If you are into it, then basically this time we are gonna be building a image classifier using the ideas of the logistic regression. Like we basically taking all the pixels and flattening it and passing it through a neural network in a sense. I mean, it seems to work a little bit, but it's not the best algorithm out there, but it will give you an idea. It will take you to a place where we will be shifting from the ANN or DNN, that is artificial neural network or deep neural networks, to CNNs, which are more optimized or which are mostly used for images as such. I mean, nowadays there are other approaches as well. Basically, CNN is kind of a feature extractor for images, right? And so let's start from there. Okay, let's go do the same that we do all the time. That is run the debug on the whole thing. I'm supposed to add a breakpoint here, I guess. Okay, so basically importing all the stuff. Just so you know, all this code is coming from a book called Step by Step PyTorch, and all credits are to the uh, creator of this book. I find this book absolutely brilliant. It takes you through every single line and it explains you a lot of stuff. And I'm also referring through uh, a website called D2L and of course Daniel and his course and few other resources that I already have updated in my Notion page. Okay, so let's get started. We have all the important libraries imported, that is the random numpy, pytorch, optimus for optimizers, your gradient descents and all that, and then is where all your models are living as of now. Function is like you want few function like softmax or something like that. Yeah, and here is our data set loader. We have extensively talked about how data set loaders and uh, how basically you are preparing your data set for the PyTorch models, right? Okay, all that stuff, and these are all the helper modules you can call them. And for visualization, we're using mac.lib and we are setting the style, all that stuff. Okay, I don't need to go through them. Okay, let's get started. Let's step in, and we are using a function called generate dataset, which is gonna be generating something, and I will show you what that is, and we will go through how images looks and what are the basic things that you need to understand about images, right? um, we'll go through it one by one. I hope it will be really nice. Okay. Okay, let's go in creating the images. Okay, that's I should have just stepped over. Okay, no worries. I'm gonna just step over that whole part and I'm gonna run the whole thing. Okay, that's it. Let's see what is images, right? And okay, I can see something. It's a 5 by 5 matrix, and apparently there are 300 images. Hmm, and it's binary. That is, we are doing classification, right? So it's a binary classification of yes or no. And so let's see the length of it. Can I do length of it, or maybe shape of it, as these are, I guess, tensors. Yeah, it's 300 images, and every single image has one channel and fiber. So how does an image look? We are going into the whole image processing kind of a thing, right? um, oh, sorry, I made a yeah. Okay, there we go. So images mostly is what? Images are one of these square boxes, right? This is your image. This is a 5 by 5 image. If I can just do this. So you essentially have 5 by 5, right? 1, 2, 3, 4, and again 1, 2, 3, 4. So now basically what you have is pixels, right? A image can be thought of as pixels, where each pixel has some intensity associated with it, right? If the intensity is high, that means it's dark, or I mean, we can map it. It says 0 is uh, dark or something, or light, let's say, and whatever the 1 is dark, right? And anything in between them is telling you how intense it is. So if something is 0.5, it is more grayish, right? um, so that's what it means. So intensity is defined by these numbers, and in most cases the intensity we have right now is basically starts from 0 and goes till 255. So 255 being the darker one, and 0 being that it's completely white or something. Okay, so if you check this one out, if you see, let's take, this is one image. Okay, uh, we can actually plot them out if you want, but let's see, let's plot this whole thing, and I can show you also. Okay, I hope you can see this, right? So if you see, check this one out, and also the numbers that is at. So okay, so in this case what we have is 255 being what you say, the lighter one. So 255 is white, and all the zeros are, there is nothing, basically it's all black. If you check out the second one, the just the last one has intensity, so you can see this one has intensity of 1. So now the task that we are defining is a very simple task. Mostly in computer vision, this we all most lectures start with classifying digits using CNNs, like basically your digit recognition. Any one writes digits, and you can recognize which digit is it from 0 to 9, something like that. MNIST dataset is the one that I think we will also be using that in the future when we are doing image classification using CNN or something. Yeah, and so now all we have to do is, if you check this out, you see the label, the dataset that we created. It says basically um label is 0, and this one has label 1. This one also has a label 1, 1, 1. What is it basically saying is the white lines diagonal, that's all. If the white lines are diagonal, or at least in this case here is one block, I don't know if we would call it bidiagonal, but okay, If that is the case, we say it's 1, or that's a true value for our whole data set. And if it's not diagonal, then if it's a straight line, then it's a 0 value. So this is 0 value, this is 0, and these all are diagonals in a sense. Okay, I hope that makes sense. So this is our data set. I think we are showing the first 30 of them. Cool. So I hope, so in this case, if the first image, all of them were zeros, right? These are zeros. If you map all that, 0 0 0 0 0, and all of them are zeros. And this guy is the only one where it's completely bright. Okay, so all of them will be black and black, and this guy is just white, just as in the picture. Okay, that's cool. Let's see now. If you have seen the shape of the whole thing, right? If I shown you the shape, which is 300 comma 1 comma 5 comma 5. So right now our image is a 5 comma 5 picture. So our image is represented as a matrix of 5 comma 5, right? And there's also one more thing added, that is 1, that is the channel number. Okay, what is channel representing is basically intensity of different colors, if you may. So there can be like RGB colors, right? If you want a colorful palette, so RGB would be a good choice. So RGB, right? There are 3 channels there, and the combination of these intensities will produce every single color that you require, right? So it can be like in our channel we say, let's say 10% of red comes in, and then 80% of uh, green comes in, and let's say 10% of blue comes in, and it will produce some other color. If you know color theory, you might know what color it's gonna create or something. So that's what it is. So in that case, if it was not just a black and white image, not just a grayscale image that we say, right? And it was something with colors, it would be having a dimension of 3 comma 5 comma 5, right? Where 3 represent the channels, and this guys are representing the matrix size. Okay, that's all. That's how simple it is. So if you were to represent them in a how I visualize it, basically it's like this: 1, and this is second channel, and this is the third channel. Okay, and see, everyone will have some blocks, right? Something, this one will also have blocks, this one one will also have some blocks. And so basically this is, though, if this guy is R and this guy is G and B, if you can think, if you superimpose all of them, okay, so this will have some intensity. So it is like 10% here, it's 80% here, and it is 10% here. So if we superimpose all of them, so what do you get? The resultant current color of that image, right? So that's how I always imagine it. So all these things, like uh, squeeze them up, and you can see how the colors are layering with each other. So that's how I imagine things are happening. Okay, and then the 300 is basically the number of images that we have. So we have 300 images in this part, right? We have 300 images, and every image has one channel, and it's a matrix of 5 by 5. That's how simple it is. Okay, we can go through that. We can see few things. Okay, let's go in. Okay, oh my god, I don't do that. Let's break it here and let's jump to the other part. Okay, let's create image. Okay, let's say this one. Okay, plotting is done. Let's move on. Image R, that we are creating the image R. Let's see, this is what it is right now. It's all zeros. We are gonna fill them up. So we are basically filling the I'm gonna be basically showing you how the RGB forms and how we can see them, so we are creating the R channel for the whole thing. So if I show you R, it looks like this now. So we will also visualize them how they look. And let's go with the G one, right? G is also initialized, and G looks like G, right? Looks like this. Okay, cool. Let's see the B values. Okay, well, we are gonna superimpose them in a sense. Okay, RGB, and it looks like this. So now let's take all of this and some percentage of those guys, and let's add them up. As I said, in this figure, we will add these guys up, right? These guys up, the intensity of this one plus this one plus this one, we will add them up, and you will get a resultant out of it. Okay, that's what we are doing. So this pixel will be result of all the pixels added up. That's what here is. So in this case, it's all grayed out. So even if I do this, it will be grayscale anyways, but it will be a combination of these intensities. So if you check, it's 500 and 255 plus 0 plus 0 for that pixel, but this pixel is the addition of 128 plus 128, and all of them are grayscale, so it will just intensify this particular pixel to a much higher pixel, right? That's all it will be doing. Okay, we can see that. Let's see, and we will stack them up using numpy image RGB. We can do that. Okay, let's plot them. Let's actually visualize how it looks. Here it goes. Okay, yeah, I hope you can see this one, right? Pretty neat. So you have R. Right now it's all grayscaled. That's it. So you see the ones with the higher values are basically bright in color, and see, it's if the intensity is smaller, it's more grayish in color, and if it's 0, that is all just black. The same behavior. Now you add them up. So as I said, this guy is adding with this one and this one, and then basically you can think of it as an average. So it will be like 5. So for this particular pixel, so this particular pixel, if I were to give me a second, yeah, so I was talking about is, you can see the resultant is 500 and 4 514, and let's see how we got 542 55. Let's say divided by 3, 84. Okay, seems like they are doing some kind of a, oh yeah, there is this value, right? You see, if I add, let's do this, just to, for my own edification, 2 point, I'm just going to take this one and add the RGB value for the first pixel. It's just this one because all other pixels are 0. So you see it's 43, if 41 or 0.2126 goes exactly like 54. So you see the 54 number here, right? For the very first pixel, that's all we're doing, right? So you can think of it like that. Okay, works. I have a pen here with me. If I can use that, I don't know. Yeah, seems like I cannot use that. What can I? Oh, I cannot. Let it be. So okay, yeah, let's get back to the whole thing. So that's basically done, and then understand. Let's try this one out. Now this is an RGB one, I suppose. Yeah, this one will have been RGB. Let's do the same thing. Let's copy this and pass it. So if it were actually colored, so this is how it would look like, right? The intensity of red, the intensity of green, how intense they are. we're defining it here itself. Only difference you see, this the intensities remain the same, we are just adding in the colors, right? And then we are adding them up and something looks like this. So if you check now, the resulting is 5 comma 5 comma 3, and here it's actually 5 comma 5 comma 1. Now, so it's basically, if an image has only one channels, it's basically grayscale image, and the range of the pixel goes from like 0 to 255. That's the key point, and everything in between is just a shade of gray, in grayscale kind of a thing, right? But if you want, grayscale is kind of like boring, of course. Maybe you want to add some colors to, so all you have to do is add colors to the intensities and then get the result out of it. So now there are two ways actually, mainly to represent colors into the framework that we are using, that is PyTorch, and these are pretty straightforward actually. Okay, PyTorch uses simple. PyTorch has a schema that goes like, and I like the schema of PyTorch more than TensorFlow. That is n, that stands for number of images, and then the number of channels, and the height, and then the width. This is the way images are represented in PyTorch. If you have already seen, we have already shown you that, right? Check this out: the number of images, the channel, the height, and the width. That's how it's. But in TensorFlow uses the only change here is it's H, W, and then C, and I find it very hard to visualize them, in a sense, because I cannot really stack them up in this way. First you are getting the images, and then you are telling the channels. It's much better to tell the channels and then the image, I feel. So I like how PyTorch does it, you know and there's one more library called PIL for images. So you can visualize image inside PyTorch, and for that, mostly it goes PIL image library for uh, Python, right? And they use HWC. So if you were to have an image that is in PyTorch, and you want to visualize inside your terminal or in your Jupyter notebook or something, you have to take that only one image, because there's nothing for the number of images, and you have to basically do a change in the dimension, the whole thing, right? From this guy has to change to that guy. It's jumping from here to here. So that's how it's gonna be if you want to visualize it using this library. Okay, and we can do that. We will be doing that. Yeah, so let's go check that out. Okay, I am done with that. Let's see, let's go directly to this part, and okay, debugging done. Let's see images. I have already shown you the shape of the images. I don't need to show you the three for the, okay, example. Taking one of the examples, that is one image. If I were to take the example and look something like this, and if I were to show you the shape, it looks something like one of the images, right, in that whole 300 images. That's it. And now if I were to change, all I have to do is do this transpose and tell which dimension you need to swap. So you have to change this dimension swap is happening between, if you see, check this out, see, the dimension swap is happening between these guys, right? This dude is going there. Okay, so we are just defining the first guy, that is this first guy. I can use a different color. This guy, that is the zeroth guy, is going here, so we will define it as 0, right? And this is 0 1 2, right? This the second element, or the index 1, is going where? Here. And then this guy is here, so you get this configuration. So that's what we are doing, simply using NumPy, and that's it. If you run this right now, goes inside, and let's see the shape of it as well, right? Example, this one, and the shape. So shape is 5 comma 5 comma 1. You can also use it for visualization using PIL. We'll do that. Okay, let's get into Torch Vision, which is a library by PyTorch for doing all kinds of stuff with images. The pre-processing happens, the dataset management, preparing the dataset, all, and also training them and using the models, all the pre-trained models also, or you wanna fine tune or transfer learning and all that stuff. You can use Torch Vision as native to PyTorch, right? Let's do that one by one. Let's look into transform. So transform is one module where in Torch Vision, where you can create this sequence of transformation that you want to take your image through, right? And let's tensorize everything. Take that example that is this example that you turned into uh, the pill compatible format, right? And vectorize it. So let's set this guy, and I want to see the shape of this guy also, just for my own edification. It is a torch tensor now with a shape of 1 comma 5 comma 5, right? Okay, now let's use pill image to actually show that image, right? All I have to do is do this and see the type of it. I can go to the terminal and show you the type. It's a pill image. Okay, whatever. And oh, sorry about that. I can do this. Actually, my Justin code is set to false. That's why that happens. It's a pretty cool stuff for debugging. Actually, I like it. All I can do is I can take this, I guess from here. You can pass it here, and you can see that one image, and I have displayed it using nothing but your pill image. That's a library for images. Okay, let's go on. Let's transform those images, I guess, right? I don't want to waste my time on this one. Okay, let's jump to this one. Okay, flip over. Okay, that's just done. Okay, let's jump over this one. Flipper. So what is it gonna do? Let's see. Flip image. Let's see the flipped image. How does it look? Flipped image is as a shape, shape. Can I do that? I don't know. Okay, it's showing error. So it's a, as of now, this sample image is a pill pill compatible format, right? So it's not compatible with PyTorch. So it's not really a PyTorch tensor anymore. So you cannot do this. You can flip it, of course. And this flip, by the flip is coming, where is coming from? It's coming from nothing but your NN formatter. Okay, so it's so you can see it's inside the transform.py inside PyTorch. Okay. Okay, we can show that also. I can do this, and let's show. We just flipped it from horizontally. This guy is literally the mirror reflection of this guy, right? If that makes sense. Let's move on. Okay. Okay. Transform on tensors. You did a transform right now on what? Pill compatible structure, like the pill image, if you're gonna call it. I'm just gonna call pill image now. But now this is your TensorFlow image. Okay. Tensorize this damn thing and show it to me. And I see now if I do image tensor dot shape, now it will show it properly. Okay, that makes sense. And if you see, they have also done a little trick that is basically, it has converted, if you see, this whole thing that was going from 0 to 255, they have squeezed it into 0 to 1. So 255 would be basically your 1 and 0 will be 0. I think I can come up with a simple derivation to for the formula, I guess. It's been a long time I've done that. So it's like take the maximum 255 and subtract it with uh, x of max minus x of min. I will look into it once. I can formulate that, not a big deal. It's actually pretty simple. But all you have to think about right now is it's just a mapping between the maximum and the minimum. So minimum stays zeros and maximum is squeezed down to 1. So everything will be squeezed down to that scales. Okay. Okay, that's important part. It's easier to train such models with uh, which has this uh, range that is between 0 and 1, instead of some random range as 0 and 255. Cool. Let's go on. Where was I? Yeah, basically it's what we call normalization in a sense, but I guess there's explicitly also going to do that. But random horizontal flip does it automatically, I guess. So if I take this into account, now if you check this one out, that is your normalizer tensor. Okay, normalize the whole thing, but it's now between -1 and 1. So -1 being the darkest and 1 being the light colors. Okay, now the normalization is basically, if I can show you the normalizations code. Normalize torch image. Yeah, let me just check where it's coming from. It's coming from transforms for a normalization. So there is a normalization, normalize in what do you say, in the NN module and also in the PyTorch vision module. So both of them are there. So now that depends upon how you are looking into it. Right now we are using the PyTorch module to do that, right? So we don't want to look into that. So okay, cool. Let's go on. So the composer is like one platform where you can tell, basically first flip it and then do the normalization or something like that, So we are sequentially applying these modification to the image using the composer. So you say compose and the composer will work, and let's say compose the compose tensor. Hopefully it is the same tensor that you see out on the top, right? This is this tensor that we got after doing it manually, and now this is the tensor that we got out of composed tensor, right? And we can also check is it if it's same or not, and they should be, and yeah, they are true. That is, both of them are actually equivalent. And let's print these things out as well. Example and example tensor. So you see now what example is and what example tensor. Example was this one, and the example tensor is this kind of scaled one, from 0 to 1. Cool. Yeah. Any caveat that I have missed out, I will just try to see if I can. So that's okay. Okay. Okay, now we are just so you know. So normalization, standardization normalization, this transformation modify the range of values a given feature or a set of features. Okay, having features in well behaved ranges greatly improves the performance of the gradient. As I already told you, if they are not in some arbitrary range from 0 to 225 that we had in the original image, but if they are in a well defined range, then the performance is better, because the it has basically better performance while it's doing the gradient descent operations, basically the updation of the uh, weights, right? And by definition, pixel value can only be positive, usually in the range of 0 to 255, so we can turn it into 0 to 1 or something, right? Now uh, yeah, so we can do this, but yeah, we can also change, as I shown you, from -1 to 1, depends upon the use case if you want to do it. So it would be something like, right now, if you have seen, like something like this guy, right? The normalizer. If you check, what is this normalize, and I'm giving the mean as, I'm gonna call it mu is 0.5, and std is 0.5 as well. Okay, so I'm giving a value of mean and the standard deviation. So now the input, if the input, that if our input is 0, okay, the formula that it comes up with is simply that it will take that input, okay, and it subtracts by the mean and then divided by the standard deviation. If you see, this is the actual standardization formula, right? From the, if you have a little bit of idea of what standardization is, we call it Z something like, right? And forget about that. All you have to do is take this, now plug this one inside it, so it will be 0 minus mean is 0.5, standard deviation is 0.5. If you see, what it is basically is -1 for if the input is zeros. So if you check, before starting this whole thing, we saw that the input was this guy, right? That was coming out of horizontal flip guy, and the inputs are 0 and 1s. So if the pixel is 0, then it will be turned into -1 using this formula. As simple as, if the pixel is 1, the input is 1, the output will be again 1 minus 0.5 divided by 0.5, which is nothing but 1. So you effortlessly changed your range from 0 to 1 to -1 to 1. All right, okay, that, hopefully that makes sense. Cool. Yeah. Okay, I just showed you how the other ones look, these guys, right? And by the way, example, I can clear, if I run this, actually, let's go inside and let's say example tensor. Example, we are converting into a tensor, I guess, and also doing this to it, basically dividing it, the whole thing, by 255. So that does the trick, right? All the zeros will be zeros and 255s will be ones. So that's what you got. Okay, let's get to compose is done. So compose, no one expected you to run this transformations, like, okay. Okay, let's talk about data preparations. So as I told you, PyTorch have already equipped you with a lot of pre-built functions that you can directly use. Let's go through them one by one. So we are taking the images. As if you still don't know images, if you don't remember, images looks like this, a lot of them, 300 of them, right? Okay, all right, and there we go. And we are just taking them, dividing by 255, so the range will be 0 to 1 exactly. And let's go through them. And labels are also there with us. By the way, I haven't shown you the labels, right? So labels, if you see, I want to just show you the shape of it. It's 300. So every single image has one label. That is, if is it is the white lines diagonal or is it straight? If they are diagonal, so if you see this, right? If they are diagonal, then it's 1. If they are not diagonal, then they are zeros. So that's the label. So every single one has one label. That's why we have uh 300 of them, because we have 300 images, right? So that's just literally an array of 300. Okay, we will be changing it to 2D because that's what we need in the future. Let's see. Okay, we'll get to that point. Okay, now let's do this. Okay, so next, we use both tensor to build a dataset, but not a simple tensor dataset like before. Once again, we will build our own custom dataset that is capable of handling transformation. Okay, it's quite simple. I think we have already done that, right? Let's go through them. This class is defined. It has a init function. It has a get item, basically indexing function, and the length function tells you the length of the stuff. So these are Dunter methods to do the same thing. We have the composer. Let's create the pipeline for that composer, right? And let's go inside this this class we just created. So we are passing in two things, that is your x tensor and y tensor. Let's visualize them, visualize. Okay, looks horrendous here. To be frank. Okay, I'm gonna just do this. We don't need that right now, so we can just do this. And let's take this guy and do this. Okay, it doesn't look really nice, but if I were to just take one of those, right, and take the first image and its label, that's what it is. This is the first image and that's straight, so the label is 0. That's what it is. Okay, we are passing all of them at once into the class, and the composer is the composer that we have, that we define literally on the top, right? You have x, that is your x train or x tensor as of now, and transpose is done. Okay, we just initialize, we create an instance of the class, and we will be using it in the future. So it takes like 3 arguments, that is your tensor for the features, that is x, and a tensor for the labels, and optional transformation. If you don't want to do a transformation, just don't pass it, because we have it in as a default. If you check, that is none, and if it's none, then it will not go inside this, right? Of course, no transformation is given, it will behave similar to a regular tensor dataset, right? And the main difference is in the get init method. Instead of simply returning the elements corresponding to so basically we are just not, if you remember from the tensor dataset, we created a class for that. Although there is a tensor dataset, directly you can import it from PyTorch module, but you can see instead of just simply returning the elements corresponding to a given index in both tensors, it transforms the features if the transformation is defined. If it is defined, we do not do this, but we do the whole transformation of the image, and then we get the image that is transformed and also the particular label for that image. So it will be like, it will just like this. If you think of it, it will give out the image and their particular transformation in a tuple, because it's returning a tuple right here. Okay, yeah. Okay, so do I have to create a custom dataset to perform transformation? Not necessary. The image folder dataset, which you will likely use for handling real image, handles transformation out of the box. The mechanism is essentially the same. If a transformation is defined, the dataset applies it to the image. The purpose of using yet another custom dataset here is to illustrate its mechanism. Just like we created a custom class For tensor datasets, we are creating a custom class for transform tensor dataset. But essentially, we have a method directly that you can use in PyTorch to do all these stuff, which we will come across. Okay, cool. So now, don't we have to like split the data set into test, and we will do all that stuff. We will see into it what it is and all that stuff. So subset random sampler. So let's get into it. So previously, when creating a data folder for training sets, we set its argument shuffled to true, since shuffling datasets in most cases improves the performance of gradient descent. This was a very convenient way of shuffling the data that was implemented using random sampler under the hood. Every time a new mini batch was requested, it sampled some indices randomly, and the data points correspond to those indices were returned, right? So basically, before also when we were doing this, I think in the classification part, we sample randomly because you don't want the first batch to have all the positive values and the second batch to have all the negative values, but you want a random sampling kind of a thing happening, right? Even when there is no sampling involved, as in the data folder used for validation set, a sequence sampler was used. In this case, whenever a new mini batch was requested, this sampler simply returns a sequence of indices in order, and the data points corresponding to these indices were returned. So okay, so in a nutshell, a sampler can be used to return sequences of indices to be used for data loading. In the okay, so the subset random sampler samples indices from a list given as argument without replacement. As in the other samplers, these indices are used to load data from a dataset. If an index is not on the list, the corresponding data point will never be used. Okay, so let's look into that. Okay, so if we have two disjoint list of indexes, that is no intersection between them, and they cover all the elements if added together, we can create two samplers to effectively split a dataset. Let's put this into code, right? Firstly, we will create two shuffled list of indices, one corresponding to the points in the training dataset, and the other corresponding to the point for the validation dataset. We have done this using NumPy, so let's do that. Okay, so now here this is a function that is been used to do the whole splitting with a random sampling. Okay, index splitter. We are basically, idea is simply that you want to split, there are 300 images, you want to split them, but also you want it to be a random splits. So let's see how you're going to go about it, right? You will also be defining, I guess, the ratio and all that stuff. Let's get to that. Okay, so what are we passing? The index splitter is passing the length of the X train. So X train, just the training part is so all the features, all the features are being passed into the splitter, and I see the ratio is 80 to 20. That is your 80 being 80 is your training data sets, and 20 is your the 20% of the whole data set is your training testing or validation data set, right? So you are creating index equals to some array idx. If you check this out, it's just an array of starting from 0 to 299, because there are 300 of them. That is the length of your number of samples, right? Number of features, whatever you call it. And then you have you are turning the whole tensors, making the splits argument to a tensor, the find multiplier, so we don't have to worry about something up to 9. So now this is basically multiplier. If you check this out, what is this multiplier? Multiplier is 3. And what is the 3 used for? 3 is used with the split tensor, and let's see what it does actually. Now if you check this out, the formula for the multiplier is simply stating that n divided by the sum of, so if I can show you that one by one, so we can actually, what is this? It's 300, right? And if you want to see this one also, it's basically the split tensor, right? You have, you basically did what? You took the percentage and you did a split on them. You are turning this into that. So 240 is the number of samples that uh, are like the 80% of the total data set, and 60 is the 20% of the whole data set, right? So you just did a split using this ratio. I hope that made sense. Okay, so if you check, if I were to show you this, so I have already run this, that's why it has shown this. If it wasn't the case, then this would have been uh, this would have been what? This would have been 100, right? This would have been 100. So because it's 80 plus 20, that is your 300. Basically n is your 300, and 80 plus this is your 3. This is your multiplier. Okay, so you're multiplying this 3 to what? Your split tensor that as of this state is 80 comma 80 comma 20, and then you get 240 out of it, and this is your 60 out of it. So that's all. That's, you just made a split. Exactly 80% of the data set is going to the training, and 20% of the data set going for testing or validation, right? And if there is a difference, throws at the first split. So add please does not complain. Okay, what is this def? What is def now? It's 0, as there are no difference actually, because what happens is sometimes you might be this equation might not properly, for example, if it was 330 or something, right, and it's then it will be 30, that is 3.3 or something, right? So if you do 3.3 into 80 or something, right, and 3.3 into 20, so you might get a kind of if I basically I can just 3.3 into 80, that's surprisingly a 264. That's a good one. 220 and 66. Yeah, but it might be that some things are left or something. If that is the case, if there is a difference between the total number of uh, data set that is there, and also you have a situation where all of them are not being accounted, then there's a difference will be there, right? So you take the 0th value and you the add the difference into it. Okay, okay, so now this is coming from your random split that is inside your PyTorch. Okay, this is not native, this is not native to Python, or not, we are not implementing it, it's coming from Python. Okay, that's done, and as soon as we hit this, let's see what happens. We have train index. Let's see, train index, and it looks like this, which is an instance of a class called subset. That's all we have as of now. And if I do train index dot indices, you can see the index right now. You see this shuffled index. I hope you can appreciate that, right? So there are right now 240 indices here, and all of them are shuffled. So we got that, what we were trying to find, right? Okay, but the whole thing can be done using subset random sampler. Now if I run this, and again I do for this guy, that's your sampler, it will vs right now instance of subset random sample, and if I do indices, it's a subset of the subset in itself. I guess then I can do indices on that, right? Yeah. You see, you are getting the same results in both the case, the one we implemented and the one the PyTorch gives. Um, I think that's pretty awesome. Cool. So, so the let's see into it a little bit more. So n is basically your number of data points. Split is the value of list the values representing the relative weights of the split size, and seed is the seed what is it, right? Okay, so PyTorch random split needs a list with exact number of data points in each split. I wish I could give a proportion like 80% or like scikit-learn has 0.2, or we can just say that 0.2 or 0.8. How much is the ratio of the training to the validation set, right? And then it would figure out how the points go into each split of it on its own. So that's the main reason index splitters exist like this. So the reasons why it exists is we have to index through this we have to split through the index, is we don't have a straightforward method like uh, scikit-learn has, right? We can give it relative weights and figure out the number of points out. Okay. Okay. Cool. Now these two are already there in, and we know what data loaders are. It gives you pairs of your it prepares your data set for PyTorch using a situation where you have the uh, you can create batches out of it, and it gives a very nice formatting where the x is and the label, that is your training features, and the labels are given alongside each other in a tuple. In simple sense, we can visualize that too. Okay, you know what, I'm going to stop this stream here and we'll be continuing in some time.